So the same thing that we just did with growth rates, we're going to take a look at them looking at a decay rate. So a rubber ball is dropped from a height of 82 hundredths of a meter. And it drops, it bounces. It's not going to bounce quite as high, but it's going to be at some rate, it's decaying, that it's decaying a little bit less. It's decaying to a little bit smaller number each time. So the first bounce, it bounces up. We started off at 82 hundredths of a meter. And after the first bounce, it comes up to 64 hundredths of a meter. So we start up here, 82 hundredths, bounces, comes up to 64 hundredths, bounces again, comes up to half a meter, then 39 hundredths, and etc. So these are the data here. So let's plot the points in a graphing calculator, or in this case, Desmos, and graph. All right, so I basically took those same points off of the thing. I just put them in here. I typed in table up here and threw in the numbers in here, changed my axes around just so I could see it a little better. Does this look like exponential decay? Is it linear? No, it doesn't follow a line. Looks like it's getting slower and slower as it's going here. So yes, this does look like exponential decay that's happening here. So yes, it is. In the third row for each bounce, enter the decay factor that yielded the bounce height. Okay, so we want to find a decay factor. What do we multiply? This is just like a growth factor. What do we multiply this number by to get to the next one? Well, how do you find it? You do the same thing that we did to find a growth factor. You take this number here and you divide by its previous number. So in this case, we take 64 hundredths and we divide by 82 hundredths. And I'm just throwing it on my calculator, and I get basically around 78 hundredths. So that's what I'm going to write right under here. For after the first one here is 78 hundredths down here. Go ahead and write that in. And then I would like you to calculate it for the next one. How do you find the decay factor for the next one? Do the next two, and then check to see. You don't have to do all of them. I just want to check to make sure that you can do a couple of these, and then we'll be able to take a look at what I have here. Okay, so here we go. These are the decay factors that we had here. Notice that all of these decay factors are less than 1. 100% would keep it the same. If we were multiplying by 1 every time, this would stay 82 hundredths, 82 hundredths, 82 hundredths. But we're not multiplying it by 1. We're not multiplying it by a number bigger than 1, because that would make this number bigger. We're multiplying it by a number less than 1, which actually makes it smaller. So we are not increasing, we're decreasing it. So now, once we take a look at all of these decay factors, how might we combine all of these decay factors into a single decay factor that is the closest approximation of how bounce height is related to the previous height? Well, pretty much the same thing that you did when you were looking at a growth factor in there. Decay factor, we are going to average them out and find the mean. All right. So what would that factor be? What would be the decay rate? All right, so that if we take the average of all of these numbers, we've got 9 of them, add them all up and divide them by 9, and we get a growth factor of 77, approximately 77 hundredths in there. Now, this is an important thing to understand, and this one's actually a little bit harder. Before we took the 100 and we added the growth factor, and we got our 100, which was a 100%, and we added the 78% or whatever it was, 77%, and we got 1.77 to get the growth factor. This time, we're going to start off with 100%. If you think about it, we want to know how much is it keeping. This number is telling us how much it keeps each time. That is the factor, but its rate is actually how much it's losing each time. And so it's decaying by, if I take 1 and I subtract 0.772 from it, I actually get 0.227 repeating, which if I change that to a percent, and sometimes you can give it as a decimal, the decay rate, or you can give it as a percentage. If I move the decimal 2 places, usually you hear it as a percentage, 22.7 repeating percent. That is the decay rate. Again, we start off with 100%. We are keeping this is our decay rate, is what we keep. We're keeping 77% approximately, and we are getting rid of, it's in terms of the bounce, we're getting rid of about 22.7 repeating percent. Okay, so what would we expect the height to be on the 10th bounce? And once again, we have the y equals a times b to the x. A is what you start off with, b is what you're multiplying by, in this case, the decay factor, and x is the number of times that we multiply by that factor. So the height we would expect to be, we start off with a height of 82 hundredths of a meter, and we're multiplying it by its decay rate, which is 0.772 repeating. How many times do we actually multiply that one by? Is 10 times. And we throw that into our calculator, we will get 62 thousandths, okay? A little bit smaller than the 9th day, which was that. Could we have just taken the 9th day and multiplied that by 0.772 to get this? Yes, but assuming we hadn't done all this work in here, how could you get just from the beginning one to the end one? We could use an equation like this to jump very quickly to find that. Okay, let's do one more application of this. People expect space travel to other worlds to take decades, if not generations, to make the trip, because the other worlds that might have life are going to be light years away. Plutonium-238 is a possible fuel source. If its yearly decay rate, and this one is not given as a percent, its decay rate is given as a decimal, is 0.00787, or it's actually less. This would be, if this was a 1 here, there'd be 1%. So this is going to be about 0.787%. How much will be left of the original? We're going to start off with 10 kilograms of plutonium, and we're going to be traveling for 100 years. Again, like we said, it took decades. It's going to be a long time to get to these worlds. Will this plutonium allow us to travel for 100 years? So again, back to here, we have to remember they are giving us a decay rate. We need a decay factor in here. So just like we did 1 minus the 0.772 repeating, we're going to go the other way. We'll do 1 minus the 0.227 repeating, and to go back to get this number. So we take the decimal that they give us, 1 minus 0.00787, and that gives us about, it looks like it's going to keep 99% of its value, a little bit more than 99% of its value every year. Okay, so we start off with, we have the amount that we're going to have at the end of the time equals to the amount we start off with, which in this case is 10 kilograms, multiplied by its decay factor, which we just found it to be 0.99213. For how many years are we going to do this? This is how much it decays every year. How many years? 100 years. We multiply that through. And actually, it's going to have a little bit less than half of its of what we started off with, 4.54 kilograms left. Looks like we're still going to be traveling after 100 years. At least we'll have enough plutonium if our people have survived for all the other problems that we could have in space out there.